Now recording is started.
I feel like it's a cue for something.
Yeah, it is. Okay. All right. So today, as I mentioned, I'll be using the same set of notes as Wednesday and finishing those up. And then I've written notes for Wednesday's class on section 1.2, and those are posted on the site. I might still edit them a little more, but at least they're there. One thing to watch for is at the end of each batch of notes, there are problems assigned, and I'll summarize those on the assignments page. So I picked out one problem for 1.1, number 4, which I need to say a little bit about. And then the Wednesday's notes, I threw a couple problems from the next section in there too. So it's a good idea to start looking into problems as we go, at least as we finish a section, so that you can keep up. So what I want to mention from the one problem that I assigned from section 1.1. Okay, and I hope we have some good chalk in here. Not really.
So all these problems will be on the homework?
Yeah, the homework is these problems.
Oh, is this? Okay.
Yeah, but I just dole out the problems as I go instead of dumping
Right.
all on you at once. Okay, so I'll turn around and switch section of the board I'm supposed to be using. Sure. Okay, so this is 1.1, number 4, the only problem from this section. First, there is a typo in part A. So what it should be is y prime is equal to minus sine x. Because it refers to example 1.2, it has a minus sign and they left it out here. Okay, and also in part A, you don't need to bother with the graphing part because that really can't be done unless you have some very nice software for doing that. So if you really want to, you can. But it's not something that can be worked out algebraically. It's what x, y values to plot. And I want to check in part B. Okay, yeah, part B doesn't have an actual graphing part to it. Things are meant to be worked out algebraically and such. Okay, and then I should have time at the end of today to talk about what you would do throughout this problem. This problem is about first integrals, which I haven't said anything about yet, but I'll have some commentary about that at the end of the section. So here's things to keep in mind for this problem. Okay. All right. Also, I've already notified the two remote students that we have that the video from Wednesday has been posted, on the assignments page, the lectures page, there's a link to YouTube to watch the video. So if you want, you can review that. I'd be interested in any feedback if there's something off with the quality of a video. I had to do some enhancements so that you can see the writing on the board more easily, but it might not have been enough. So I think I'll need to actually watch my font size and such to make sure that everything can be read. But I want to make sure that all that can be seen. Okay. So what I'm going to do for much of today is continue with examples of dynamical systems. So, one example, all the examples I've done so far have involved only 2 equations, but here we have a 3D example. So our variables are plus x, y, and z. So most of you who haven't had me in class before, that's how I do my z's in order to distinguish them from 2's. Also, for my notation, I often use something like this for partial derivatives, so these are not 2's either. So, okay. That's something that's come up in several classes, actually. Okay. In multivariable calculus, I actually had a student thought that these just canceled out. So, okay. So b prime is minus 1 minus. Okay. Okay. B is a constant, and it's equal to 2 pi over sinh 2 square root of 2 pi's. Right, so it's not an arbitrary constant. Okay. And the domain of this problem is the unit cube which I'll use that notation for. So the interval 0, 1, Cartesian product through x, y, and z. Now, the idea is this dynamical system is meant to model heat flow. Okay. So some terminology involving heat flow, since we'll see examples of this from time to time. I have a function, I'll call it S, of x, y, z gives you the temperature profile throughout the domain. Then the heat flux is equal to minus the gradient of S. And the reason for the minus sign is that the negative of a gradient, you might remember from multivariable calculus. What is the significance of the negative gradient? What does it tell you about the behavior of a function? Okay, so if you're looking at the gradient at a particular point, and how the function is going to behave if you travel in any direction from that point, it might increase, decrease, etc., or stay stationary. What?
Outward or inward flow?
No.
Do you have to do something with partial derivatives, no?
Well, the negative gradient is a particular direction of significance. Well, what sort of behavior is happening in that direction?
It's a negative gradient, so it's falling.
Yeah, steepest descent direction. So the gradient tells you which direction the function is increasing most rapidly. Negative gradient gives direction of the steepest decrease. And then any direction orthogonal to that is direction along which the function is not changing at all.
Right.
Level curves or level sets. Okay. Now, so flux is often associated with a derivative or a gradient because this is often associated with some sort of velocity vector. But by convention here we use minus the gradient because this is heat flow. So if you remember from the more elementary science classes, which I know were a long time ago for all of us, that heat energy flows from what to what?
Hot to cold.
Hot to cold. All right, so it's flowing in a direction of decreasing temperature. So we want a decrease in this case.
Right.
Yeah. So okay. So this gives the actual direction in which the heat energy is most likely going to flow. Okay. So
That's so awesome. I love it so much.
okay.
That made my day a little better.
Well, good. I'm.
Hey.
Yeah. Well, besides, you're not the only Minion fan in this room.
Huh?
You're not the only Minion fan in this room. So, okay. Yeah, I'm waiting a text message on a 102 student, but that was not her. So there's going to be more Minion sounds to come, so you'll all just have to deal with it. Okay. All right. So, but the thing is, what's the gradient? The gradient is derivatives with respect to x, y, and z. So, so the heat flow lines, or you can also think of them as streamlines, satisfy that x prime is equal to minus ds dx. So keep in mind this notation, often used for partial derivatives. I'll either write it this way, partial of u over partial x, or use the x as a subscript. So I'll probably most likely use the subscript just because it's easier to write, but I want you have to be aware of that right away. Y prime is minus sy, z prime is minus sz. So what we'd like to be able to do is, we can easily solve this system if we can recognize that this right-hand side is a derivative of some function with respect to x, and this is a derivative of the same function with respect to y, and this is a derivative of the same function with respect to z. So what you can do is, to see if it works out that nicely, is actually try taking this first one and integrating it with respect to x, and then integrating this with respect to y, integrating this with respect to z, and keeping in mind that when you integrate with respect to x, y, or z, you're going to have, they're not plus c's. Like for instance, if I, oh, still not the right, still not the text I'm waiting for. Someone I follow on Twitter actually said that she thought that hell is full of minions, and I was
Why? They're so happy.
I know I was just so outraged by that, but I promise I'll never get into a Twitter fight with anybody. So.
Not worth it.
I
Nice one.
almost put that reference, but now that you've done it, he's gonna get mad at me if I do it. I'm already ticked off enough people today.
Apparently, I've gotten enough text as it is from outside this room.
Sorry.
Yeah. But,
Do you have different message tones for certain people?
for a couple, but I haven't gotten around to picking for.
Okay, so like you wouldn't easily distinguish if like I've texted you. Yeah.
Right.
Okay.
Right. Yeah. So. Okay. Anyhow. Yeah, of all times to get, I didn't think I'd get many texts during this class, even without inside jobs, but apparently I am. Okay, so if I integrate this with respect to x, what I need to do is add on a function, an arbitrary function of y and z. So that's like playing a role of your plus c. If it this be plus something of x and z, and then this plus add-on function of x and y. So if you go ahead and do that and just try to match things up, and then these are relatively easy to integrate with respect to x, y, and z because, for instance, I would treat these as arbitrary constants and just integrate that, and the same for the other two. So what you end up getting, if you carry out that integration procedure, and I'll just write down what it is, but if you want, you can try convincing yourself that it really is right by trying it yourself, is f of x, y, z is x plus, this is from integrating the 1 in the dz dt, and then you have cosine 2 pi x, cosine 2 pi y, 2 pi z, all over sinh 2 square root 2 pi. And actually, this is not entirely right because I should be able to add on some some arbitrary constant, and it would still satisfy all three equations.
So by integrating z for -1, you get an x.
Well, okay. Yeah, if I integrate this with respect to z,
Oh,
Should be negative.
should be z.
did I write it down wrong?
It says.
I mean, because, I don't know if it's a negative z or a z, but it should.
Sorry, that is a z.
And then should it be positive or negative?
It should be positive here because notice I have a minus in here.
Oh, okay, gotcha.
Yeah. Okay. Are my notes wrong? Yes, my notes are wrong.
I didn't do it.
I don't have a number.
Yeah.
Yeah, that's someone else that I was not expecting to hear from. And I just read your text, Haley. So.
Are you just adding your the each integral together?
No, what you do is, okay.
How are you getting that?
So what the idea is, so you're saying s is equal to the integral of, like, whatever you're given for x prime, dx, so you work that out, plus, I'll call this function g of yz. But then when you get it, there are two other representations of s.
xz.
Yeah, xz. And then you get one more, z prime dz plus,
Is that whole thing an integral? Is it not just on the, or is the integral just on the x prime d? Okay, yeah.
Yeah. So s is equal to all of these, so you match them up. And what happens, the z term, you're only going to see it from this one. And the thing is, because then if you take that and differentiate with respect to x or y, it goes away. That's why you don't see it at all in here. Yeah, so the idea is you set them equal to each other, and that lets you figure out what are these supposed to be. In certain number classes, like it definitely came up in multivariable calculus, but it also came up in 285 of differential equations, problems where you're having to do this kind of integration to. That's what I'm waiting for.
So we need more frames.
What?
Oh, you're gonna put on silent now, right?
Yes, I am, especially knowing you guys. All right, I'll be back in a couple minutes. Ready? I have 40 minutes left. Okay, now if we actually want to go back to the original equations. Now, of course, with any dynamical system, it's a good idea to determine does the dynamical system have any fixed points? Are there any x, y, and z that you could plug into this so that all three equations are equal to 0? So for instance, from the first equation for dx dt, how could you make that equal to 0? There's more than one way, but
Repeat what you just said?
for dx dt, how could you make that equal to 0? What points could you plug in?
For that x prime.
Yeah.
You what?
Well, x equals 0.
If x equals 0.
Yeah. Keep in mind, x, y, and z are confined to 0 to 1. So you only have to think about that.
What's it?
So yeah, x being 0
It's in the whole
or x being 1.
one.
Or it's-
Yeah,
yes.
it's not. It's a whole bunch of.
Um, Yeah, now the thing is, and what about y?
Cosine 360 is 1. So you got, well,
Y equals 1 or just 1? Wait,
No.
no.
no, because
No,
that's
right.
2 pi is 1.
It's gotta be, yeah. So it's gotta be
No, not
0.
half.
Yeah.
0.
No.
Well, so it's
Wait,
still
hold
1.
on.
It's still 1.
Do you remember any trig at all?
It's gonna be pi over 2.
I gotta draw my,
No.
you can circle my head, hold on.
Well, yeah, the argument to cosine has to be pi over 2.
Yeah.
But y equals
Less than 1.
1/4.
1/4.
1
Yes.
Yeah.
And?
I
What's
thought you
the-
said it had
Yeah,
to be
1/4.
0 or 1.
Yeah.
Yeah, 1/4 or 3/4. Well,
Okay, yeah, pi over
yeah.
4. Yes,
Ninety.
that's what I meant.
okay, and then x can be, alright, so I'll write these down over here. Okay, so
Oh,
x
it's between 0 and 1.
is 0 or 1, y equals 1/4 or 3/4. And what about z?
You mean pi, right?
Um,
Oh, the pi is
yeah, pi is included, so.
Oh, okay,
Yeah.
yeah.
So what about z?
1/4 root 2.
No, z actually has to be 0. The sinh hyperbolic sign is 0 only at z equals 0. So that covers this first equation. But then you have to do the same thing for the second equation and the third equation, and you have to take the intersection of all of those. So for instance, for a y prime, you're going to get the opposite. You're going to get
X equals 1/4.
yes. So yeah, x 1/4 3/4.
Y equals
Yes.
0, 1.
So that's kind of unfortunate. But he still gets z equals 0. So z equals 0 is still a candidate. So then you have to go down to this equation. And the thing is really, so then if you go ahead and let z equal to 0, cosh of 0 is 1. So then you have to find x and y so that what's left of this is still going to be 0. So it turns out that you can find a fixed point. It's rather difficult to find. You actually have to try to find it numerically, but it only happens when z is equal to 0. So one thing I mentioned in the notes is there are no fixed points in the interior of the cube. The only one is that you can find is on the plane z equals 0. So the bottom face, and it's in the interior bottom face, and it has to be found numerically. So basically, you said this part equal to 1, and then you solve where this is equal to 0. And I started doing it numerically. It's kind of a pain, but it can be done. So the behavior is not so interesting just because the fixed point, the only one you get is on the boundary, which actually the book neglected to mention. It just said no fixed point. It's like, that's wrong. The book is wrong in a few places, unfortunately. We'll figure that out as we go. All right. So heat flow application is one that will come up from time to time just because of its importance. And in all those cases, we'll be usually dealing with sort of temperature profile, and the flux is given by minus the gradient. Now, another example that comes up in I'm only going to mention it briefly now, but we're going to study it in much greater detail when we get to chapter 2. But I just wanted to put it out there. Now, no, actually, wait. Whoa. Two-body problem, gravitational force. Now, I'm going to write this as two ODEs, but the unknowns in these ODEs are vectors, three-dimensional vectors. And these expressions may be familiar to you, depending on how much you remember from physics.
The gravitational equation, right?
Yes.
Yeah.
All right, so we have Newton's second law at play here. Force is mass times acceleration, second derivative. And here are the expressions for the gravitational force. And to explain the notation, because m's mean mass, R1 and R2 are position vectors for the two bodies that are exerting gravitational force on each other. And R12 is equal to the magnitude of the distance between these two locations. Now, keep in mind, you know of gravitational force, you may remember being proportional to the square of the distance. And here we have it cubed. Why is that still correct? And it's,
There's another R somewhere.
yeah, up top, right here.
Right there.
Yeah, because you could factor out the magnitude and keep a direction, and then cancel the magnitude of one of these down here, and it's proportional to 1 over distance squared. So it's still consistent with that. But even though we have two ODEs that are written here, this is really 6 ODEs, because you can have one equation for the x component, y component, the z component of this, and then x, y, z components of this. So really I've written 6 ODEs. And this can be written as a system of 12 first order ODEs, because you can introduce new variables corresponding to the, so you have variables corresponding to your unknowns, the x, y, and z components of R1 and R2, and then you introduce new variables corresponding to their first derivatives, and then you can write down 12 first order equations. Now, so to get an idea of what that system would look like, so if I let R1 have components x1, y1, z1, and then R2 is x2, y2, z2, and then I introduce new variables, u1, u2, actually I'll do it this way. I don't remember what the book does, but I'll use u, v, and w. So u1 is x1 prime, u2 is x2 prime, and then v represents the derivatives of y, and then w are the derivatives, velocities for z. So, in fact, these are the first 6 equations of my system of first order ODE. So I just wrote them down, just defining these. And then, for, okay.
You want to do A,
Well, actually, go the other way around. So, so my 12 ODEs, I just write these in the opposite order. So x1 prime is u1, x2 prime is u2, and then I'll handle x now. So then u1 prime, which happens to be equal to x1 double prime, I can take from my original system. So that's going to be, well, in fact, from this system, you can see that the M1s are going to cancel out. So let's go ahead and do that. So I have G M2, and then here I just have a difference of x components. So that's going to be x2 minus x1 over R12 cubed. And then I have a similar equation for U2 prime. Okay, so here are all my equations pertaining to the x-coordinate. And then I'll have similar equations for the y-coordinate. So V1 prime is GM2, Y2 minus Y1 over R12 cubed. GM1, Y1 minus Y2, and then 4 more equations for Z that are totally similar. All right. Now, once you have your dynamical system written as a first order system, like the previous examples, they were already given to you as a first order system. If they're not, you go ahead and convert. So that's true of any higher order equation or higher order system can always be written in a as a first order system by the introduction of new variables that represent the lower order derivatives of your unknowns. In this case, we just need the first derivative. So that's why throughout the semester, we may have some second order applications or second order examples, but we're always going to be studying exclusively first order systems because we always can. Okay. So one term that's going to be of importance now and then is the called the phase space. Unfortunately, throughout applied mathematics, phase space is used for different things. Actually, I should mention phase space in this class has a totally different meaning than phase space from your honors thesis, so unfortunately, I just tossed that out. Actually, I like that one better, but oh well. So phase space is the domain of all of the dependent variables in your first order system. Emphasis on first order. So, for instance, in the previous examples, ones from Wednesday, it's just the appropriate domain for x and y. And in this heat flow example, you also throw in z. In this case, we're dealing in 12-dimensional space because we have 12 variables. So for this example of phase space is equal to R6 corresponding to the new variables, Cartesian product with all of your possible position vectors, R1 and R2. But you have to keep in mind, where are your time derivatives defined? You have to go back to your original equations and check, are they defined everywhere? And you have to exclude any place where they're not. So for instance, any of these equations, where would the right-hand side not be defined? And what could,
R is 0.
yeah, the distance between them.
Yeah,
Where R12 is 0.
Yeah.
So you go ahead and exclude that. So the phase space for this problem is almost all of R12. You just have to exclude that one-dimensional slice. Or I guess it's really a three-dimensional slice because you're equating x, y, and z. Okay. Okay. I haven't chewed up all my time, but So any questions about converting to a first order system or phase space? All right. This recording has gone a whole lot more smoothly this time than last time. And will be more entertaining this time than last time. Okay. Okay. Now, the next example, we have a swinging pendulum. So we have some string, and we have a weight on the string, and the pendulum is allowed to swing really through whatever angle it wants. In fact, what you could do is I could take this weight and hold it up here and let it drop and swing back down. So it's allowed to move pretty much anywhere around this focal point here. So the equation of motion for this is so if theta is the angle that it makes with a vertical. So think of a vertical as corresponding to theta equals 0. So the equation it satisfies is the second order equation, where k is a constant. And what I can do is, same as in the last example, I can convert this into a first order system of two equations instead of one second order equation. So I can say theta prime is equal to v, you think of it as velocity, and then derivative of velocity is theta double prime, and that would be minus k sine theta. Now, the right-hand sides of these equations are defined everywhere. So the phase space for this problem is all of R2, for our two variables, theta and v. Now, although effectively we're really concerned about theta between 0 and 2 pi, but you can actually plot solution curves for all values of theta from minus infinity to infinity. Okay, but the problem with this situation of modeling a pendulum using this equation is it's not really physically accurate. For example, suppose I take this weight and I hold it over here and I let it drop. This equation assumes that the weight is going to swing in a circle back down towards this position. But if I hold it over here and I just let it go, physically, what do you expect to happen? Yeah, it's going to drop straight down. There's going to be slack in the string, which this equation does not bother modeling. So it's vertical, it has vertical drop until all the slack in the string is taken up, and then it will swing back and forth. So this equation isn't really realistic enough. So what I'm going to do is we're going to constrain its motion and think of this instead of a weight on a string, we think of this as a ball in a hoop, which this equation would accurately model. So if I have it over here and let it go, it's going to stay along this circular path with radius equal to the length of the string. And then we can study that dynamical system to at least get a first order approximation, if you will, to the behavior of the pendulum. Okay. Now, let's take a look at fixed points, where the of this system, where the right-hand sides can be equal to 0. So where does that happen in this case?
So theta equals 0.
Theta equals 0 is one of them, but keep in mind, v and theta, what's our phase space? It's all of R2. So what other possibilities are there?
K equals 0.
Well, k is some fixed non-zero constant.
Okay.
So,
Okay. Okay.
So we're dealing with values of v and theta. So what do v and theta need to be to make the whole right-hand side 0? Or actually, I'm going to switch this, theta and v.
2n minus 1 pi over 2.
I'm sorry, what?
2n minus 1 pi over 2. To get it.
Wait.
But 2n minus 1 times pi over 2.
Oh, you're thinking of cosine.
So
it's
it's
0.
n
Sine
pi.
is
0 and 2
I had trouble parsing it into a fraction, but okay.
0 and 2 pi.
yes.
And
2 pi. 0.
So the 2n
0
Well,
pi,
4
2
pi.
pi.
and
N pi. Well,
It was
2n pi.
Some-
no, not 2n pi. N pi.
N pi.
Any integer multiple of pi.
But anyway, yeah.
So I'll use k pi for k is an integer.
Where is it?
K is
Are you
already,
using K?
yeah. So,
Oh, dang it. Okay.
So we
Shoot, I gotta change my notes again.
N.
Alright, okay.
And then V is some constant.
Well,
But v
But
is
these
automatically
variables.
0.
yeah, v has to equal 0, just to make this side 0.
Okay. Okay. Yeah.
Yeah, so v must be 0, and then any multiple of pi. So in your, so I start drawing the behavior of solution curves. All I know is at each of these multiples of pi, there's a fixed point anyway. Okay, it's not quite to scale, but get the idea. Okay, all along the, okay, so here's theta and here's v. So the theta axis, the selected points along the theta axis are the fixed points. But now, as far as the behavior of this ball in a hoop or weight on a string at these fixed points, well, here the vertical corresponds to 2k to n pi. Whereas, what about the odd multiples of pi? Where are they? Where does this debate correspond to?
In between.
Nope.
The other side left.
Top. Yeah. Up here
Okay,
is
top,
theta
yeah.
equal
Okay.
2n plus 1 pi for any integer. Okay. Now, let's think about the behavior again physically. What would happen if we moved the ball or weight to the appropriate position down here, up there, and then just let it go? So if we have it down here and we let it go, what's going to happen?
Gravity.
Right, but since it's held on a string,
It's already just gonna say
yeah, it's just going to stay there. Nothing's going to happen. What if I hold it up here and then let it go?
It's going to come back to 0.
It's going to come back down. It's going to move a lot. So what happens is when theta is an even multiple of 2 pi, corresponding to down low, that is called a stable fixed point. Because it is not, if it's at that fixed point, it's not going to move very much. In this case, it doesn't move at all. But it's going to tend to stay around that fixed point. On the other hand, if we have an odd multiple of 2 pi, that is called an unstable fixed point. And we're going to study fixed points more as we go. But it's important to realize that you can have very different behavior at these fixed points. That the solution tends to either be drawn to them or to be pulled away from them. And actually, those of you who are currently taking 560, the term is going to come up there too and have pretty much the same meaning. As far as being able to converge to these fixed points or diverge from them. And in fact, if you were to plot streamlines or solution curves, it'd be not easy to do. You basically have to do it numerically. But you would see very different behavior depending on whether it's an odd or even multiple pi. So the even multiples, the stable fixed points, you basically get a certain orbital behavior near the fixed point. But then what happens is, let's suppose V gets larger and larger. Then what ends up happening is this is constrained between minus k and k for whatever k is. So in other words, the v component of the velocity vector is bounded between minus k and k, whereas the theta component, the horizontal component of a velocity vector, is free to get larger and larger. So what ends up happening is as v gets large enough, you have these wavy solutions that become closer and closer to horizontal lines. And similar to one of the examples from Wednesday, this is going to become a dominant component. So as v is larger and positive, it's going to be horizontal line to the right, and over here to the left, tending more and more towards a horizontal line. Okay. Now, what's interesting is here we have these wavy solutions that just keep going from minus infinity to infinity, or vice versa. But down here we have orbital solutions. So at some point, there's actually a transition between the two that passes through these odd multiples of pi. So solutions that behave like this or like this. Okay. So these curves in between, there's a term for that. Separatrices. So these mark the separation between streamlines that have this very different behavior, orbital versus nearly linear or linear.
That graph is very similar to the line of
The other one.
you drew it the other
Number
day.
2, right?
Yeah.
Yes, it actually is. Yeah, there is very similar behavior. Sorry, what?
Is there like a major difference? Is it the same it should be?
Let's see, because the system in that case is, well,
We learned about that streamlining.
yeah. Okay, the difference is that really this equation we have in the first example is a cinch, whereas here it's just linear. But so the real difference would be because in the previous example that one was growing exponentially, whereas this is growing linearly. So the rate at which this becomes like a horizontal line happens way faster in the previous example. But yeah, the overall behavior, because what's happening is when v is small, Since V is similar to V, for V sufficiently small. So in fact, closer to the horizontal axis, the behavior is almost exactly the same. And it will also depend on the value of K, of course. But yeah, there's a reason why, looking at the functions, why you actually do get that similar behavior. Okay. Now, and unfortunately I'm running out of time. But I do want to cover one more example. So what I'm going to do at the start of next time is talk about stuff that's directly related to the one homework problem from this section, about how you find what are called first integrals of these kinds of systems. So you can try to get an implicit solution. Because depending on the equation, you're going to use techniques that you would have seen way back in 285. Some of those can be kind of a pain. Okay. So this is just a change of the previous example. All right. So now what you do is you still have your ball in a hoop. But now what you do is you allow the hoop to rotate along this axis. So that's definitely going to complicate the motion a bit. So what happens is, and you have to be more knowledgeable in physics than I am to see what this equation is. So I'm going to actually just use a gravitational constant here. So that's from the previous example, same thing. But then I add on an extra term. Okay, where what's happening is, if I look at this from above, here's my hoop, is allowed to rotate through a maximum angle A, and the B is a frequency with which it rotates. So that's where the constants A and B come from. So what you can do is, you can write this as a first order system, like before. So theta prime is equal to V, V prime is equal to all this. But there's one complication that makes this system harder to analyze than the previous ones. And that is, unlike the other ones, we have a direct occurrence. This depends on time directly. So this system is non-autonomous. Because an autonomous system is where your time derivative depends only on your dependent variables, not your independent variable. And we prefer autonomous systems. They're much easier to study. For instance, only for an autonomous system does it make sense to talk about fixed points. So here's what you can do. You can take any non-autonomous system and make it autonomous by adding another extra variable for time. So I can say tau prime is equal to 1, so then tau itself would just be t. And I can fill in tau in here. So that makes the system autonomous. So I can take, so anytime t creeps into my time derivatives directly, I can just add this one extra equation, and now I have a three-equation autonomous system. So now I can study it like any autonomous system, except now it's in 3 dimensions. And, but here's what you do. You want to study solution curves of your original system. So what you can do is you can get your solution curves in in 3D, and then you flatten them 2D. So you have your 3D. So you have your 3D picture, and you just. I'm standing in front of a camera. 3D solution curves, and you just squish it into two-dimensional plane. And here's what happens as a result. Your solution curves are very likely to cross each other. So that's one important property about solution curves or streamlines. If your system is autonomous, your solution curves will not cross each other, or they will not self-intersect. That's really what the term I'm using for. So I better be more precise about that. It's impossible to happen. And the reason why is you're going to have you have to have a uniquely defined velocity. But in this case, if you take something that's 3D, within 3D space, yes, they won't self-intersect. But then, once you flatten it, all bets are off. And you're going to have these self-intersections. So, yes?
What exactly, the arrow where you have it says made autonomous, where are you pointing to?
Oh, the tau.
And the top one that says made,
So,
No.
okay,
Non-autonomous.
this was T.
it was T and it's changed to tau. Alright, I got you.
Yeah, so this is a time-dependent lecture board.
Okay, I got you.
Okay. So the nice thing is, even though there are many different kind of systems we can study with very different behavior, first order, higher order, autonomous, non-autonomous, we can always think in terms of a first order autonomous system, and that's why we'll spend most of our time on that, because at least you can always reduce it to that case. Now you might have very many variables, and that's kind of a pain, but at least that simplifies the theory involved. And I am 3 minutes over time. So, but those will all be examples of dynamic systems for now anyway. So I will talk about how to try to implicitly solve these things, which is important for homework, first thing on Wednesday. Now I get to listen to all the crap you said during the intermission.
You can have one.
For your entertainment.
Thank you.
It's gonna be
You're
fun.
welcome.